So let's look at a two-tailed situation of hypothesis testing. Here we have an example where let's get a highlighter out. So a new postal delivery system is trialed in a city. The postal service watchdog wants to find out if this new system has changed. So it's not an increase or decrease, it's simply whether it's changed. The moment they use that wording, you know it's going to be a two-tailed hypothesis test. The next day delivery rate from the previous value of 80%. A survey is conducted 20 letters. The survey showed that 18 letters were delivered the next day. Let's set the said 10% significance level whether the new system has changed the next daily rate. Right, so let's start by defining P. So we'll say let P be the probability the letter is delivered the next day. Is delivered the next day. And what we want is a hypothesis, a null hypothesis, and the null hypothesis is basically that P equals 0.8. Now, our alternative hypothesis is that there's been a change, so therefore P does not equal 0.8. And we've been given a two-tailed test. We've been given a significance level. Let's write that down. Significance level equals 10%. Now it's worth probably pointing out here that this here is now two-tailed because it's not a greater than or less than situation. It's simply a not equal to. So we need to define x. Let's define x to be the number of delivered in terms of P. So it's the number of letters delivered. So I'm going to say oops, I'll just bring it back my black pen. Let x x be the number of letters delivered the next day. We have x, and we then state that if h0 is true, we then say x is binomially distributed with n being 20 and P success, letters being delivered next day is 0.8. Now, since this is a two-tailed hypothesis, there's two methods we can solve it with. One is, let me write this down, method one is simply to use the using just probabilities, and if we can imagine the distribution pretend the distribution looks something like this. We know on this side we must have 5%, and on this side we've got another 5%. So together they make up our 10% significance level. And so therefore our 10% over 2 just give us 5% either way. And for the upper tail, for 18, we're measuring against 18 letters being delivered. Probability x is greater than or equal to 18, would therefore be equal 1 takeaway. The probability x is less than or equal to 17, which equals 1 takeaway 0.9, 0.79, let's correct that, 39, which is 0.2061. Okay. Now, and so we can say 0.2061 0.2061 is in fact greater than 0.05, and since it's greater than, we accept the null hypothesis and conclude there is insufficient evidence that the new system has changed the next day delivery rate. So let's write that down. There is insufficient evidence to suggest the new system has changed the next day delivery rate. So that's using the probabilities. We can also use critical value approach, and like I said, the critical value, critical region approach is sometimes, you should know how to use it. It is something that sometimes comes up in exams. And so we're looking for, let's write down critical value approach. So in here, given that we've got 5% either way, we want the probability x is less than or equal to a is less than 0.05, and so we want the highest value of a, and we want the highest value, and then we can also have, obviously, the probability where x is greater than or equal to b is less than 0.05, so we want the right hand tail, in which case we want the lowest value of b. So from our tables we can read, and I'll bring out a copy in a minute, that the probability that x is less than or equal to 12 gives us 0.0321, and the probability that x is less than or equal to 13 gives us 0.0861. So we know it lies within that region, and since it lies within that region, the one that's less than 0.05 is obviously 12. Therefore, we can conclude the highest value of A is going to be 12. So anything below there will be our critical region, and so therefore our critical region is when x is less than or equal to 12. What about for the other end, the right hand side? Well, we've got the probability x is greater than or equal to b is less than 0.05. That's the same as the probability of x is less than or equal to b minus 1. And we can rearrange that to form the equation where we've got that less than 0.95. Again, if we then extend our tables, go back to our tables, we should be able to see that that region in fact lies between 18 and 19. So let's say we've got 18, 0.9308, and the probability that x is less than or equal to 19 gives us 0.9885. So where it's less than, the highest, the lowest possible value, therefore we can conclude the lowest possible value of b minus 1 has to equal to 19. And so b equals 20. This is actually, what we're actually looking for is a value which is greater than 0.95. So there's a, we correct that, so that should be 0.95, and you want greater than. Obviously, when you rearrange that, so the 1 comes out, that's right. So you've got 0.95, and it's greater than. So so the one where we're looking for is where it's greater than will be that 0.9985. So we end up with b equals 20, and so therefore we know that the critical value is when x equals 20, and the critical region is when x is greater than or equal to 20. So let's write that down. Critical region is when x is greater than or equal to 20. Now, we know that we've been given there's been 18 deliveries. So for x equals 18, for x equals 18, obviously that doesn't lie in either critical region. So we'll just say this doesn't lie in either critical region, and therefore we can accept. Therefore, we accept H0, and we can conclude that there is insufficient evidence to suggest that the new system has changed the next day. So, in summary, what we've got here is a two-tailed approach, two-tailed problem, and because we're looking at change. One way you could do it is just look at critical values and just say whether your probability is greater than or less than. So, the method one is just look at the probabilities and see if it's greater than or less than the probability, your significant value. The second method is actually to find the critical values, the boundaries, and determine the critical regions and find out if your value actually lies within that region. Some exam paper questions actually want you to work out those regions. Okay, so as here's a visual representation of what's going on. And we can see here there's two tails. One region, we can see the 0.05 lies between 12 and 13, and the lowest value it can be is 0.03. And similarly on the other end, we've got 0.95 is between 18 and 19, and so therefore we've worked out that the value x will be greater than in the critical region will be 20. And so our critical regions lie between x is less than 12, greater than 20, and we had 18 as the number of successful posts, and that obviously doesn't lie in the critical region.